Good afternoon, everyone. Uh, I would like to introduce you to both Codasip as well as myself and our university program. Uh, Codasip was founded in 2014 through a PhD dissertation on how to automate the design of custom processors. And then RISC-V sort of came into being at the same time, and it was a good combination of their technology that came out of the university as well as RISC-V. And between that, we have some very nice opportunities. And to set the stage work, back in the 1980s, I was working for a company called Soulborn Computers, and we were designing a custom processor. And I'm going to call that a golden era because a lot of companies were designing custom processors in the 80s. Hewlett-Packard, which I also worked with, we have different architectures such as x86, ARM, PowerPC, HPPA, VAX, Alpha, and many other computer architectures. We were about ready to tape out our first processor, and then Sun Microsystems came to our company and said, no one's going to buy your custom processor, and that's not what a startup would like to hear. And so they explained it is because software was becoming really important, and unless your company could guarantee that you would have at least 10 or more years of software support, that they would not port their software to our architecture. So we actually changed our architecture, and we became the very first Sun-compatible SPARC processor. And what happened was, after that golden era ended in the 1990s, computers architectures shrank, and the two biggest ones that survive today are the x86 and ARM. And they are closed architectures. We can't really take a look inside the architectures and actually even modify them. Both Intel/AMD and ARM has a tight control of that, and that has provided some really good value to people by actually enabling software or binary portability from one ARM vendor to another. But it does limit our innovation available to us. So because the processors were closed, it was very difficult for universities to research inside the processors. So the universities and companies started to figure out how to add intellectual property around the processors, but not inside the core. Now, in the 2022, we believe that we're in a new golden era of processor engineering. And that's because a combination of two things. First of all, we have RISC-V, which is an open instruction set architecture, which enables access to all. Small and large universities, small and large companies and startups now have access to the architecture to implement into their FPGAs or to ASICs, and not just to implement the architectures, but if we add to the architecture, not subtract, we now have binary compatibility. Now, if we use a GNU Linux and we don't take any of the features of the x86 basic instruction set away, my processor can run that. But if I add new instructions to provide value in terms of the application, I have access to the existing binaries, but I can also provide value by customizing my processors. Now it gives an opportunity for really to look inside the processors. And my job at Codasip is really to prepare for the next generation of processor engineers. That's my sole job, is to get more engineers graduated both out of undergraduate as well as master's and PhD. So let's take a look at what is the university program. And it has three pillars. The first pillar is to spur innovation, to solve tomorrow's computational problems through promoting research. So the university program, we are working with universities globally to spur research in processor security, functional safety, real-time embedded systems, intelligent memories, and artificial intelligence. We're not looking at just spurring the innovation on the peripheral of the processor, but actually opening up the processors and adding features into it. What we like to call is tightly coupling the application into the processor to make a domain-specific application more valuable in terms of performance, energy, cost, or whatever metrics is important to that application. But the university program is not just spearheading research, but we're also creating curriculum content to augment education. My experience from teaching at the university level here in the United States, I'm creating an undergraduate course material as project-based learning. Students through this program will have access to RISC-V cores and also access to electronic or processor design tools to actually implement a 5-stage pipeline. There will be a curriculum for master's and PhD students to actually modify and integrate RISC-Vs into system-on-chip solutions and for their research. And then our third pillar is we are going to be creating, this will be starting more in the fall time frame, an open exchange of knowledge and mutual support to create an environment that will encourage interest to be processor engineering and accelerate new solutions. By being open and free sharing of ideas, we believe that is a key thing of spurring innovation. Basically, Linux did that into the software world. Now, one of the key areas in research, get back to what I mentioned before, is when we have these closed architectures where the researcher or professor or corporate researcher, if they wanted to look at a problem, they could really look at only two of the problems that they could actually touch or influence. One was optimizing software algorithms and external hardware. And where these two circles overlap is where they could actually do some optimization for the particular research that they were doing. The processor was something they could not touch because it was a closed architecture. I could not get inside the ARM. I could not get inside the x86. But now, with RISC-V, we are breaking down that traditional research barrier. We can actually start bringing in the processor optimization into the problem. Now the researcher in academia or in industry can actually start figuring out how to optimize all three: the processor, the external hardware, and software. One example I'd like to use as just a simple example is if you're concerned about single bit errors. Now, you could actually maybe add some hardware externally to somewhat monitor a processor, maybe even have a 2-to-1 voting system, multiple cores to check if one has a soft bit error, majority rules. But why not just get rid of the idea of software errors and by just integrating error detection and correction inside the core? And so I have this little example where you can actually add like hamming encoding on all the data going to the register file and decode it as it leaves. And that only took me a couple hours to add that functionality. Once again, that's an example of tightly coupling the application, functional safety, into the core. Not trying to do it in the outside core, but trying to optimize the core itself. So we believe today we're entering this new world where we can break down the traditional research barrier and enable processor optimization into the researcher's domain. Once again, this is my example on the hamming encoding. Now, what makes the ability to break down that traditional barrier is, once again, being able to have RISC-V cores, which is an open architecture, so you can look inside and modify it, but also having the right tools that you can actually go and modify it to the application for acceleration. For example, performance profiling, but it's the combination of the two which is the ability to break down that barrier. Codasip we actually designed RISC-V IP cores, and we also have an EDA tool that's fully integrated that enables you to modify your RISC-V cores or to pull in your application. So with the combination of those two, it gives Codasip the ability to offer the researchers in the universities a new tool in researching new ways of how to increase or provide provide additional security for processors or performance enhancements in artificial intelligence. Now, just a little bit of example of the tool chain. It's a unified tool chain. And so the tool chain from Codasip, which the professors and the curriculum, the students would have access to, is unified. It has an assembler, disassembler. As you define a new instruction, the C compiler knows it. Because it's a unified tool chain, if you make a change in one part of the design, it is reflected in all the other components. So if I add a new instruction to accelerate or maybe even protect a part of my design, when I rebuild the C compiler, now it has that new tool, that new instruction that will be used to compile the application. But to analyze, you need to have actually tools to enable you to profile the application to see where you can speed it up. And therefore, you also need simulators and software debuggers. But we're just not a tool to simulate architecture. We can actually create the actual, what we call cycle accurate design, which is a high-level abstraction using our language called Codal, to actually define what your actual design will look like. And then we can actually translate that into RTL. Once a professor at the University of Colorado went to a conference and they asked me to do a presentation at the class. And within that 50-minute session, I showed the class actually how to add a MAC into an integer-only RISC-V design in the instruction accurate model, and how that would be reflected in the compiler, and then actually change that in the cycle accurate model. And then by the time the 50 minutes was over, at the end I said, this class was just learning how to do Verilog. I said, okay, I'm going to convert that into Verilog. So I clicked the RTL button that you see in the bottom there on the right, and roughly 5 seconds later, I had the entire Verilog of the entire processor completed. And as the story goes, is the professor, when he came back, all the students were asking, why are we learning Verilog? We should be looking at a higher level of abstraction. Higher level of abstraction provides value of increased productivity and actually reduces errors as well. Now, what is the university program supporting to the researchers? We are providing a what we call a Codasip Studio, which is our development environment, which has that unified tool chain. But we'll also be providing, where it makes sense with the research, the proper IP cores, so that you're starting your research with that level of RISC-V design to start with. That you don't have to develop your own RISC-V processor. You can start at whatever particular IP that makes sense for your research. The university program is part of what we call a Codasip Lab. And Codasip Labs is developing technology, and we will be sharing where appropriate this technology with the researchers. Because once again, our entire goal is to raise awareness and increase research in the area to solve tomorrow's computational problems. So we are looking at a partnership with universities to help spur innovation along. The research support will actually be coming from the labs, which I think is very important, because we're creating our own support for professors, because the questions that professors have in their research is a lot of times different than maybe a customer would have with a looking at a production type of core. Even though we're providing production cores, but we're going to be more geared towards actually answering the questions that researchers are helping or needing to be addressed. Now, if we take a look at the curriculum side, here's our roadmap. So this fall, we're going to have all the material for project-based learning for computer organization, which is a undergraduate computer architecture class. We're also planning to have a system on chip graduate level class. for those professors that want to maybe change from an ARM-based course, SOC, to a RISC-V, but also have the ability to teach the students how to modify a core, for example, to enhance an application. But next year, we'll be moving forward with an advanced computer architecture class for graduate students in computer architecture, including out of order, Tomasello's algorithm, and so forth. And all those three classes are really augmented classes where we'll be providing just project-based learning assignments for the professor to add into their curriculum. But we are actually looking at developing our first complete new class, and that's processor security. We think there's enough interest that we're getting from professors asking us about processor security that we're going to be looking at developing a full course material to provide to universities for processor security. And in the following year, we'll have an advanced computer architecture course on multi-core, bus snooping, and then we'll also have our second brand new class, which would be functional safety. All this material, access to our EDA tools for the researchers, for the students, all the curriculum support, all the research support is for free. We're doing this to actually spur innovation and get more students to graduate. We believe there is a need for more engineers and interested in designing processors. So the curriculum, once again, it is a project-based learning set of materials where we'll be providing the learning outcomes, we'll be providing the assignments, there'll be a grading rubric if the professor would like to use a grading rubric. There will be videos to help the students understand the assignments. There will also be videos to help the students to work through the assignments if they have issues. We'll be providing all this material to the universities that would like to partner up with Codasip to basically help, once again, improve or get more students excited about being a processor engineer. Now, here's an example of, once again, the computer organization class. It is based upon the David Patterson and John Hennessy book on computer organization. You do not need to have your class based upon that textbook, but if you have it, the terminology that in the assignments match a lot of what is taught in the book, so it does match up quite well with the students. It's basically a 12 assignments, and a professor could take all 12 assignments, or possibly the first 8 or the last 4. There's different combinations of learning outcomes in those different assignments, but we allow the professor to make a decision on what they would like to have that's best for their students. One of the feedbacks that I got on this class, which we've been actually, which I started 4.5 years ago, is that from another professor who's taught the class, is they say the real learning is not in the theory or the lectures, but actually doing it, for the students actually learning and actually seeing what a data path is, how instruction decoding works, how data hazard and data forwarding works. That the real learning is actually doing it, and that's the entire idea of this, is to create a deeper learning through actually implementing the lectures that they see in class. And the system on chip is really not a 15-week class or 12 assignments like in the undergraduate one. It is a system on chip where the students can download a RISC-V processor, and if they don't want to do any modification of the core, it's just a soft core that they could actually have in their SoC. But we'll be providing assignments, if the professor would like, where they could actually start, for example, profiling an application and learning how to add resources, for example, instruction, or some other type of resource to the processor to enhance the functionality of that design, and then create the RTL and then revalidate it with the improvements of the processor. So it's really meant to provide a soft core RISC-V for the students but also then enable for a 1 or 2 week assignment where the students can actually learn how to optimize the processor and actually do that. The fall 2023 class is a class that I'm getting some feedback from professors that would like to have an out of order execution class. And what we would like to target on that is do out of order. So it's sort of like the undergraduate, where the undergraduate is 12 weeks, 12 assignments over 12 weeks. This will probably be similar, maybe 8 weeks or 9 weeks of assignments, but the students will be doing much more complicated computer architecture, such as implementing out-of-order execution, Tomasello's algorithm, speculation, and branch prediction. So this will be a much more of, once again, a graduate level course where the students get to take the theory that they're learning in lecture and actually implement that through project-based learning. And when I started at Codasip as head of the university program, January 1st of this year, my first thing I thought I should do is create a university program mission statement. I'm not going to read this entire statement, but I do want to just point out the last sentence, because I think this is the important thing, is the mission of the university program is through the support of both students and researchers. The university program aims to prepare the people and advance technology to solve tomorrow's technological challenges. I think what makes our university program unique is that we are focusing on the researchers and the students, both undergraduate and graduate students, to provide an environment to enhance the learning, get students excited about being processor engineers, and spur innovation by enabling researchers as well as students to look at solving problems differently by integrating the application and modifying RISC-V cores to support their end goal or research activities. And my last slide is just as a reminder, is that we have 3 main pillars of the program: supporting research. So we want to enhance the research through making our tools available and IP cores available. We want to support curriculum by both undergraduate and graduate. Our real goal is to, over time, provide course materials available for all the different years at the university. And also, we'll start later this year on the ecosystem to accelerate innovation by creating an environment for students and professors to share ideas. We're looking at developing hackathons or contests for the students to solve problems in computer architecture. And I would like to close off the presentation today with just a couple pieces of information. If you'd like to sign up for the university program, there's the website at Codasip. If you just go to Codasip, so there on the top menu bar, you can click on University Program and sign up, and that will send me an email, and we can engage, and I can talk to you a little bit more about our research support as well as curriculum support. And I do have a monthly blog that I put out, and one of the ones that I just put out a month ago was on how today's engineering students will become tomorrow's processor engineers, which is the university program. But I also have blogs on breaking down the university or the research barrier as well as the unified tool chain. So there's a lot of good information. Codasip is really focusing on supporting the researchers as well as our future students. So I want to say thank you very much, everyone, for your time this afternoon.